And those control totals are then sent into the land use model here, and the land use model then sends out the detailed locations of every single type of agent or household or firm inside the study area. Now we have a pre-processing step here and a post-processing step, but these are both using Cube Voyager scripts. So in general, if you're currently a Cube Voyager or TP Plus model user, you should be able to pick up these examples and easily understand how this process is working to take the input tables, which are some of them in simplified and GIS-based forms, and interpolate them and turn them into the tables that are then used by the Cube Land module, which is just another module inside of Cube, and it can connect to all of these other elements in the flowchart, and we use Cube Voyager at times just to build some of these tables, and then we can send these tables on the output side out to geodatabases. And here you see an example of using Python and Cube, for example, to take a shapefile and copying it to an output geodatabase. So we can build in Python geoprocessing and all kinds of complex operations into the overall land use forecasting application, which is sort of built around Cube Land. So then, of course, Cube Land produces households and jobs by zone, which is our traditional zonal data file, or Z data file. And this is sent into trip generation, and trip generation proceeds in basically the same way it always did. So it's a very sort of standard process from there on out. But the idea is that although the trip generation process itself isn't necessarily sensitive to transfer costs, the inputs to trip generation in terms of households and jobs by zone are in fact forecasted as part of this overall model process. And right here, in this case, we're doing a within-year feedback loop where for a given forecast year, we continually reevaluate household and firm location based upon output congestion until we reach equilibrium between transportation and land use. And that's just one way of implementing this. As you can see, this is all put together using our flowchart, which is a very flexible interface, and you can actually put in other kinds of feedback loops where you loop forward over a series of years and use the output of one year in terms of congestion as the input to the next year in the series, and so on and so forth. So we can do dynamic disequilibrium models as well as within-year equilibrium models. So right now I've got my growth scenario here, and for this growth scenario, I have an easy-to-use applier interface, which is much more sort of straightforward than the developer interface I was just showing you. Of course, the appliers don't really want to mess with the flowchart. They don't need to have to go into scripts or anything like that. They just have a form-based interface for setting up the values of different parameters and the input files and data to be used. And the most key one here in this case, for this scenario, nothing else is changing in the growth scenario. We're still using the no-build network and the base public transport lines, but we've added some growth. So the idea is this input file here with the N-agent column includes some increase in the number of households and firms by type. And that input might come from some kind of macroeconomic model, or might be coming from a spreadsheet, set of projections from our county or regional or state demographer, who knows. A wide variety of sources could be used there, and you would use whatever is most appropriate for your region in that case. And this is sort of a cooking show approach, so the idea is that we could save this and then run this model, and if I go to my window here, I can, at the end of this process, output this kind of a map, which is shown here in our ArcGIS window, and this is actually an ArcGIS map document file that's completely compatible with ArcView or ArcMap or your ArcGIS desktop software. And so the land use transport modeler can output this kind of a map, including these charts and graphics representing, for example, thematic maps showing total employment by zone, or pie charts showing the distribution of housing types by zone, with larger pies representing a greater density of housing units in the particular zones. This is just an example of the kinds of maps with legends and scales and so on and so forth that we can generate here. Now I'm also going to show you some examples of using this SAM interface to develop alternative transportation scenarios and testing the land use effects of those scenarios. And this is really an aspect that's been missing in the past. We've had systems that have been able to certainly look at the effects of land use on transportation. That's basically just straightforward trip generation calculation using assumed land uses. But looking at how transportation is going to affect development patterns when we build new facilities or make improvements to the infrastructure or services is kind of a unique function of this kind of model. So we look at our future road scenario here. What I've done, and I've already set it up in this case, and the tutorial, of course, walks you through this process, but basically we have a build network as opposed to our no-build network. And the idea behind this build network is we've completed some projects or roadway facilities that are constructed in the network. So I'll go to my window here to my build scenario. And this is the build network. I just already happen to have it open, but you could actually go to the scenario here and click the Edit button to open in the GIS window. And I'm going to zoom in on the area where I know that I built this project right here, and this is again in our GIS window. Of course, these networks can be overlaid on top of each other. Both of these are real Cube Voyager networks, but they're displayed inside our GIS window because we are storing them in a geodatabase. And if I unclick on the build link here, you can see that in the no build version of this network, we had a facility missing here. In this case, I always tell the story that this was the result of a bridge collapse somewhere in Cubetown, and we decided to finally rebuild the bridge in the build version of this network. So we've added a new link here, and we can easily go into our future road scenario then and click Run to go ahead and run this scenario. And this just brings up our task monitor. This is pulling the networks in from the geodatabase, and it starts running the models, doing initial pre-processing as well as running the CubeLand demonstration model. And what we're going to see here, if you watch this task monitor as it proceeds, is it actually feeds back between land use and transportation 3 times before reaching what we consider to be an equilibrium. So in your case, it might be more iterations than that. It might be fewer. This is a 25-zone model, so it's pretty fast, all told, in terms of computing land use and transportation equilibrium. But you might have, different results with more zones or fewer zones potentially. While this is running, let me just talk about the future transit scenario, which operates in a similar manner. So here we have our no-build network, but we're considering public transport improvements stored in public transit lines in the geodatabase as well. So everything's stored in the same geodatabase here, makes for easy scenario management and transfer of files to our GIS assistants in the GIS department. And if I go to the GIS window in which I've opened my public transport lines, here's the no-build version of this system, and we have one line in particular here I'd like to focus on, which is this one heading into downtown from the south, and I'm just taking a look at its attributes using the Feature Explorer. And it had a headway, in this case, of 15 minutes for the AM peak, 20 minutes in the off peak, 15 minutes in the PM peak, and so forth. It takes a rather circuitous path into downtown. So in the exercise, what we've done is just recode this line. So it's no longer taking the circuitous route. Instead, it just heads directly into downtown. And if we inspect the headway just by clicking on the attributes again, we can see that we've cut the headway in half, so the frequency has been increased here of service. We basically got double the frequency here in this case. That little error message is just complaining because I have my geodatabase open in 2 different environments, so don't try that at home. Always close down the geodatabase before running the model. But anyways, we should still nonetheless be able to view the outputs of this scenario. So to do that, I'm just going to go back to my future road scenario and take a look at our land use forecast. Francisco, are you there? I hear some audio. Maybe Francisco's talking in the background. I'm not sure. Okay. Okay, so these are the outputs for this forecasted road scenario, but we can also look at outputs another way if we take a look at this land use comparison shapefile, which is part of our outputs folder for the land model. And this is a shapefile, but we set up Cube to just open shapefiles in the ArcGIS window here inside of the user interface. So it'll just open up in a moment. And we can quickly compute or set up and draw a thematic map which will show basically the change in households. So if I go to post thematic map, I can use an expression based upon one of the attributes in the attribute table, such as households, and this should give us the change in households between the growth scenario and the road scenario. And so you can see here areas where the number of households went up, colored in red, and areas where the number of households actually went down. And basically what's happened in this scenario, let me just change the color scheme to make it a little bit easier to see. I'm going to make red the negative and green the positive. And so you can see here that what's actually happened as a result of completing this roadway, which was roughly in this zone right here, but we could overlay it if we wanted to, is certain locations have actually gotten more attractive and others have gotten less attractive because we have improved accessibility here in the region or the vicinity where the roadway was built. So we get a clear comparison of which areas became more attractive when we built a new transportation facilities. Okay, so that's basically the gist of this demonstration. And again, of course, if you like, you can walk through detailed step-by-step process to run these scenarios yourself using this tutorial. So I encourage you all to go ahead and take a look at www.citylabs.com tutorials.html and try this out for yourself. Now, continuing on, I'm going to talk a little bit about comparisons between different kinds of models, which if you're walking through that demo, you might be thinking to yourself, sure, this does this, but how is it different from or similar to other kinds of land use models? Why should I use cubeland? Or in what situation should I use cubeland as opposed to something else? And I really like to think about different kinds of urban models in terms of issues of geographic scale. And I see out there that we have sort of like macroeconomic models that really deal with forecasting trade and population flows within and to and from an entire region. So there are some examples of these out there. I apologize for naming some commercial products, but these are obviously, the trademarks of other companies, and I should say that right out. But Remy is one, Rimbrio is another, but there are also publicly available agencies that do this kind of forecasting. The state demographers and economists and so forth who prepare projections for counties do this all the time. We also have micro-level tools, scenario visioning tools they're sometimes called, or sketch planning tools that are really intended to try to show detailed parcel-level land use. So some examples of these are UPlan and CommunityVis, which I'll talk about later on as well. But the idea here is that the macro-level tools really don't have the level of geographic detail required to integrate directly with a transportation or travel demand model, and the micro-level tools really are almost too fine-grained, or they provide a lot more geographic detail than you need in order to integrate with a travel demand model, and in the process actually lose some behavioral and economic realism, because these micro-level tools generally tend to be a lot more rule-based because they add so much more geographic detail. You have to sacrifice some economic or behavioral complexity most of the time. And what we're trying to achieve with a cubeland is a scalable tool, if you will, a meso-level tool that's suitable for regional planning of the kind that metropolitan planning organizations and transportation planning agencies do. So really what we're trying to address is household and firm location within the region primarily, first and foremost. And cubeland is a perfect tool for doing that. And as I mentioned previously, it's scalable, so we can use zones of any size geography, but especially transportation analysis zones.